Good morning, everybody. Well, let's see here. Got Aaron coming on. Okay, guys, so I'll go ahead and get started. It's so strange not seeing anybody. I'm still getting used to that. Well, I'm never going to get used to it. So, welcome to lab. We're going to talk about the UV-VIS Lab, and I want to start with a picture of the data that we're going to be handing out to everybody. And the data are here, and you'll have to make the graph and stuff, but it's pretty trivial. And basically, there's a graph of the absorbance spectrum in the ultraviolet of ethyl acetate. This is a simple ester, yeah. And acetone, this is ketone. 2-propanone is another name for it. And then toluene, it's sort of this slightly lower symmetry aromatic compound. And then here is a mixture of these three molecules. So on the y-axis here, we have absorbance, right? On the x-axis, we have wavelength. And you can see that these mixtures are acetone in a transparent solvent here. It's actually acetonitrile, which has very little absorption in this wavelength range, but that's not super important right now. But there's acetone, ethyl acetate, toluene, and then a mixture of those three in in acetonitrile. So the question that I'm posing for y'all is, can you tell me how much of each of these three components, acetone, ethyl acetate, and toluene, are in the solution that gives us this yellow spectrum, this mixture, this unknown mixture spectrum? And I want to take a quick poll right now and see how many of you can tell me at least one of those components right off the bat.
I guess I'm just kind of confused by the question.
Okay. So the solution that gives this yellow spectrum has some acetone, some ethyl acetate, and some toluene, as those
Yeah.
three components in it. And my question for you right now is, just by inspection, can you tell me how much of one of these three components is in the mixture?
Oh. Wouldn't there be 0 ethyl acetate, like once it hits like a little after 245 nanometers?
Ah, okay. Excellent. Excellent comment. May I pick on you a little bit, Abby?
That's fine.
Okay. Everybody, enjoy, because I'm going to pick on Abby a little bit. I know. Okay, I'm going to shut up. So, so there is in each of these, each of these spectra represents a cuvette, a single solution, right?
Yeah.
So concentration doesn't change along this axis. This is just like the color of the solution that you're looking at, the intensity of the color.
Right, but aren't absorbance and concentration directly proportional?
Absolutely, they are. And everywhere that we look, this formula A equals epsilon BC applies, right? So, and in fact, I don't know if this one is. So, and we can say that the absorbance is the sum of the three absorbances, right? So it's epsilon of A times C of A plus epsilon of B times C of B plus epsilon of C, times C of B, C of C rather, right? And then there's a path length in there. But if we let's just assume that path length is 1 and sort of cancel it mathematically here. And this is the formula, right? And I haven't included lambda here, right? The wavelength, right?
Yeah.
But it's just a color, right? And so that at any given color that you look, the absorbance of the unknown is equal to the sum of those three extinction coefficients times their concentrations.
Okay.
So if you inspect this, if you just look at everything, look at the legend there, and tell me how much of any one of these three components makes up this golden spectrum here.
Yeah, I still.
Okay, all righty. Gavin, can you help here? Sophie? Oh, Vincent, you know the answer to this, right?
If I remember, it's only 1% acetone, or?
Uh-huh. Mm-hmm. Exactly. So this spectrum here is representative of a mixture that has 1% acetone.
Oh, that's really small on my screen.
Oh, sorry. Geesh, I'm sorry. I have a big screen here. But hopefully you can sort of. The idea is that acetone standard, right,
Hmm.
corresponds to this unknown mixture at all these wavelengths out here beyond about 280 nanometers.
Right.
So the only way to have that is if the acetone concentration in the unknown is equal to 1%.
Okay, that makes sense.
Good. Excellent. So let me see here. So what if the acetone concentration were 2%? In the, well, let's say that the standard, oh God, this is really awkward how to say this. Hang in there just a sec. Oops. What if the standard acetone at 1% gave a spectrum that was twice as high? In that case, what would the acetone concentration in the unknown be?
0.5.
Yes. Alexis, what do you think? I'm randomly picking them.
The 0.5?
Yeah, exactly. Exactly right. So, I love things are awake at Alexa's house. Nobody's awake here. So I just arbitrarily multiply the absorbance of the acetone standard by 2 there, just to sort of make this point, right? All right. So so you've already got one of the 3 components, right? You know what concentration of acetone right? You know that for sure right now, right? So what's the next component that we could analyze in this mixture?
Toluene.
Yes, exactamundo. Why did you choose toluene, Abby?
Because it also kind of matches at certain points.
Mm-hmm. Exactly. That's good. Why not ethyl acetate?
Because its shape is pretty much different than
Right.
our unknown.
Right. So one might suspect, oh, is there even ethyl acetate in there? Well, in this case, yes. And the unknown here is this spectrum is derived from an unknown that contains only these 3 and only these 3 absorbing components, right?
Mm-hmm.
So if you look, so for example, if you look at 285 nanometers here, can you determine the amount of toluene using the absorbance at 285 nanometers at this fairly red wavelength here? It's fairly the right-hand side of the spectrum, I mean by red. Vincent, what do you say there?
Sorry, can you repeat that?
Of course. So, can you determine the amount of toluene in the unknown spectrum using the absorbance at 285 nanometers? Using the absorbance at this wavelength right here, hopefully you can see that.
Yeah.
You can do that.
Shouldn't it just be 0 absorbance?
Excellent point. Okay. So you have thus entered the hot seat. And who wants to pick on Vincent? Nicole. You want to pick on Vincent? Yeah, you do. Come on, Nicole. Please. Oh. Okay, all right. So Vincent, does concentration depend on wavelength?
You said no, or it does, but in this case,
Okay, hold on. So, if I have, let's say I have made you a drink, right? And that drink contains um, one shot of bourbon, right? And it's just bourbon and water, right? And I say, hey, Vincent, can you look at the color of this drink and tell me how much bourbon is in there? And let's say that you knew the exact spectrum of bourbon and you knew the path length and everything. Could you tell me that? Possibly. Is it possible to do that?
sure.
Yeah, absolutely. So now if you look at a long wavelength where the bourbon has no absorption, can you tell me the bourbon concentration? If I suddenly, instead of your eyes seeing the entire spectrum, if you can only see at a wavelength where the bourbon has no absorbance, can you tell me the concentration of bourbon without tasting it?
I don't think so.
Exactly right. You can. But but then if you go to a wavelength where you can see the bourbon, then you can tell me the concentration of bourbon, right? Because you can sort of measure the absorbance with your eyes and say, oh, that's about one shot, you know, of bourbon in here, right?
Yeah.
Perfect. So now, does that mean that the amount of bourbon changed?
No, no.
Exactly right. So if you I'm picking on Vincent right now, right? Because Vincent's excellent to pick on. Thank you, Vincent.
It's just like ice cold all over again.
I know. It's a life pattern, Vincent. I'm sorry, but uh, so really, the wavelength does the concentration depend on the wavelength that you observe at?
Yeah.
Okay, so it does. So if you look at a wavelength where there's no absorbance, can you say there's zero concentration?
Oh, sorry. No, sorry.
Okay,
I
good.
forgot about that point.
Yeah, exactly, right. So the concentration has nothing to do with this. This is just, this is just how we look at it, right? So, so then what we can say here is that um, what wavelength might we use to assess the amount of toluene in this mixture that's represented by the golden spectrum here? Miguel, why don't you take a stab at answering?
Around 260 kind of overlap.
Where they overlap here, or over here, or over here? Tell me the best of these three. Would it be this wavelength, or this wavelength? I don't know if you can see my stupidly small little mouse cursor, but there's this wavelength, this one where there's the sharp peak for toluene, or out here at 285, let's say.
Right in the middle.
Hmm?
Can you hear me?
You're
I,
very
I, I
muffled.
I heard something, but I couldn't make it out.
Let me see.
Me now?
I can hear you. I can hear you, yes. So do you want to use, say, 255, 270, or 285 nanometers?
Would it be the two peaks in the middle, the one that are sharpest?
You want to use these two wavelengths. Excellent. Okay. So now, again, focusing on this golden spectrum, how can you estimate the concentration of toluene in this mixture with the golden that produces the golden spectrum? You have this standard here, right? You have the standard for toluene, which is this gray line. Then you have the mixture here, which is the golden line. And I'm sort of like, I'm just asking, which of these two, or how do you combine this information to get the concentration of toluene in the mixture that produces the golden spectrum?
Not sure.
Okay, so let me ask you this: is the absorbance of the mixture greater than or less than the absorbance of the toluene standard at this wavelength, at 270 nanometers here? So basically, I'm asking an obvious question, but I wanted to sort of slow down your mind so you can see something clear here. So this is actually 268 nanometers, absorbance of 1.5 for the mixture, 268 nanometers, absorbance of 1.35 for the 0.05% toluene. So based on this piece of information, would you say that there is more toluene in the mixture than there is in the standard?
Yeah, because higher absorbance.
Yes, exactly. Okay. So, I have one question for you, however. What about the acetone?
The acetone at that exact same
Wavelength. Yeah.
wavelength.
Yeah. If there's 1% acetone in this standard, how much is that contributing to the absorbance at this wavelength?
The same amount.
Okay. And so the same amount being like the amount measured. Sorry, go ahead.
Well, like the same amount that we found, like the 1% that was at the unknown at 285, would it be?
Okay. Yeah, the concentration. Well, let me go back to Vincent's question. And I'm sorry, this is getting a little ponderous. But does the concentration of the acetone in this mixture change as we look at it at different wavelengths?
No.
So does the absorbance due to acetone change as we look at it at different wavelengths? Does the absorbance,
At different wavelengths.
yeah, the absorbance due to acetone. So here's this golden spectrum, right? And it has three components, right? It has toluene, acetone, and ethyl acetate.
Yeah.
So in this golden spectrum, does the contribution to the absorbance due to acetone change as we look at it at different wavelengths?
Yeah.
It does, doesn't it, right? So at 268 nanometers here, how much of the absorbance is due to the acetone in that unknown?
Mm.
Would it?
So how much of the absorbance here, how much of this 1.53
Is due to that acetone.
is due to acetone, right? How much of that is contributed by acetone? How much of that is from the acetone? How much, this is a darkness measurement, right? This is darker as it goes. How much of that darkness is from the acetone? And how much of that darkness is from the toluene? So let's ask the first question first. How much of that darkness is due to acetone only?
At that exact same wavelength.
Yes.
Would it be whatever absorbance acetone has at the exact wavelength?
Okay. So this is 0.82 here. Should I use 0.82 there?
Mm. Not sure. I don't know.
Okay. Gavin, can you contribute to this?
It's 1%.
Are you there, Gavin?
He's in the chat.
Oh, shoot. I got to find the chat. Hold on. I'm so stupid here. Let's see. Where's the chat? Where's the chat?
Alt H?
Okay, Alt H. Ah. Oh, I don't understand the question. Okay. So Gavin says about 50% acetone. Okay. And then I don't really understand the question. So let's clarify the question a little bit and sort of where I'm going with all this. The only thing there's just three numbers that we want out of all this: concentration of acetone, concentration of ethyl acetate, and concentration of toluene in the unknown mixture, right? So Abby determined that there is what percent of acetone in the unknown? Abby?
1%.
1%. And you know that because, why?
It matches like perfectly for the last like half of the graph.
Exactly. Where the absorbance due to toluene is
It's just not even there.
exactly, and the absorbance due to ethyl acetate is
Also not there.
not
0.
there. Right. So in this color, all of the absorbance from the unknown comes from acetone, and all of the absorbance from the in the mixture comes from acetone. That makes sense, Miguel?
Yeah.
It's kind of like saying, you know, it could be red, green, or blue, right? And we could have amounts of red, amounts of green, and amounts of blue. And if we're looking at the red, and the acetone is the only part that absorbs in the red, and we know the amount that it absorbs in the red, then we can know how much acetone is in the unknown.
Mm. Okay.
Okay, so Gavin, harder question for you. If we look at wavelength of 268 nanometers here, right at this peak, how much is acetone contributing to that absorbance of 1.48 at this wavelength of 269 nanometers here? How much is acetone contributing? Gavin.
He's probably typing.
Oh, a small amount. I like it. Okay, it's a small amount. The difference. Okay, what's the difference? The difference between what and what? Give me two colors. How about the Spartan colors?
Why the Spartan colors?
Gold.
Well, no, but the gold is fine, but why is the blue relevant?
So let's see here. How much is acetone contributing, right?
Yeah.
The difference. Okay, so I say that because acetone is contributing this amount, it's contributing this amount here, then it has to contribute that same amount everywhere.
Right.
If I am right,
Are you?
right? Okay, so I've got Abby, Vincent, Alexis, Miguel, and Gavin. I'm trying to reach Nicole and Sophie, but I don't know if I'm going to get them. So if I want to know, for example, the amount of absorbance, the fraction of this 1.53 value that is due to toluene at 268 nanometers, that value is going to be, right here. It's going to be 1.53. So the contribution from toluene is going to be equal to this guy right here, 1.53, minus 0.81 equals something.
Okay.
It's 0.2, 0.73, 0.72. Right? So now if we go up to here to this spectrum, the toluene spectrum, you can say that 0.05% equals 1.34, then what percent equals 0.72? Right? Oops, not 5, it's what percent? What? Okay. What percent
Nope.
equals 0.34? No, 72.
I think I know the answer.
Okay, and what percent?
0.1%.
So it's it's almost exactly double that. It seems a little bit not so precise, but yeah, it's about 1%. Yeah. Because 0.72 times 2 is 1.44. Right? So it's maybe point, 0.095 or something like that. It's about 0.1, right?
Wait, what numbers were you multiplying?
I don't know.
Like I was good up until that exact part, and then
Okay, so I'm doing math here. I shouldn't try to do math here. I'm just gonna muck it up. What percent of that should be what percent of toluene gives absorbance equals 0.72, and we're talking about at 268 nanometers.
okay, at the peak.
Right, at the peak.
What percent of toluene gives an absorbance of 0.72?
Yeah. If 0.5% gives 1.34 absorbance, So
Oh,
so it's about 0.1%, It's about, because 0.72 times 2 is roughly 1.34, right?
yeah, okay, that's what I thought. Okay,
It's close to 0.1%, right?
okay. It turns out I was actually right there with you the whole time. I just didn't realize it.
Oh, good. Excellent. Excelente, San Clemente. All right. So, Miguel, how are we doing?
Yeah, following along. The 1%, the 0.1 is still I'm still kind of iffy on that part.
Okay.
So
So,
0.05 is 1.34, and that's from the at that absorbance.
oh shoot, it's not 0.1, it's half of that, right?
Yeah,
0.05.
Oh, I thought.
Darn it. Oh, Vincent,
Yeah.
you messed me up. Vincent.
Oh,
Vincent, you messed me up.
Okay, that makes more sense.
Oh, okay. My bad. Yeah. I had it reversed. Yeah, I should have
No,
had.
it's not. Oh, it's 025.
Okay, that makes sense. Never mind.
025. Yeah. I'm gonna
Half of
blame Vincent here.
0.05. Okay.
I can't do ratios, so I'm gonna blame Vincent. Okay. So how about Gavin? Does this make sense? Yes or no question? Gavin. Yes, yay. Excellent. All right, so Nicole or Sophie, are you gonna weigh in here or are you not there? It's okay, I don't care, I'm just checking in. I assume they probably fell asleep. Somebody wrote me yesterday, Scott, I'm so embarrassed, but I fell asleep during your presentation. Do you have the Zoom video? And I'm like, oh geez, I totally understand, A, and B, I'm gonna try to get the Zoom videos out there. I think they should exist.
I've
I
done
love
that for a
you.
different class. So,
Yeah.
oh yeah, I fell asleep and then I woke up after class ended, but I was still the only one in the Zoom call.
Oh no, the only student.
Yeah.
The question is, did the teacher fall asleep too?
No, they were gone too. They just left me in there.
They're like, Abby.
They didn't even vote me.
Oh yeah, Professor.
Yes, yes. Yes.
Sorry. I wasn't
No.
here yesterday, but so was this data something that you gave us, or is it?
I just have to pop it over to Canvas.
Okay.
And basically it's just gonna have absorbance wavelength, like those 4 columns, and then I'll give you the information about the standard concentrations, and you guys can.
Okay. Thank
So
you.
yeah, so so let's move on here and let's try to formalize this a little bit, if you guys don't mind. So, oh god, this is so ponderous. Let's go back to the lab manual. So here's the lab manual, blah bitty blah bitty blah.
Don't see it.
And yeah, can you see it?
Nope.
It'll appear in a sec. So, can you see yet, Abby?
No.
When you change the picture completely, it takes a second to refresh. But basically, the absorbance from the 3 components they contribute independently, because there's no there's no interaction between the different absorbers.
Can
And-
there ever be?
Oh yeah, there can be interactions, but you know, I don't even know how to. We could start analyzing that, but that's sort of like, it's not the type of thing that one would, you would think, oh shoot, they're interacting chemically. Let's do something else to measure them, right? Let's try to measure them with mass spec or infrared or something like that could get around the interactions. Oh my gosh. So so the 3 solvents here, A, B, and C, are all absorbing, right? And then the mixture also that independent sum, right? And so we know the standard absorbances here, AA, AB, and AC. Can you guys see this, for example? I guess, I don't know if Abby can see it, but hopefully.
I still see your Excel
Yeah,
stuff.
same here.
Is so weird. Oh, wait. Maybe there's some weird thing that, okay. I gotta go to video. No. Because it doesn't share the video. It shares. You share. Let's see here. This guy. How about now?
There we go.
Oh, that is so weird. Okay, so I'm used to it just sharing the video feed, but this is actually sharing different windows. Okay, so the standard absorbance spectra here. This should actually say standard A, right? Standard B and standard C, right? They have an absorbance of a function of wavelength that's equal to epsilon times B times C, right? And we actually know all of these things, right? Because we know the absorbance, we measured it. We know the concentration because we made it or we got it, right? B is 1, and the extinction is just the ratio of A over C, right? So we can calculate the extinction. And so that's true for all of these three components here. Now, the diluted mixture here, it has a measured part A, a known part epsilon A, a known part epsilon B, a known part epsilon C. Then it has three unknown parts, Ca, Cb, and Cc. And these are the concentrations in the mixture, right? Ca comma M, right? Make sense?
Yeah.
Okie dokie. So, so how can we use these equations to get to these three unknowns? These are basically the unknowns here. Oops. I'm going to try and I want to highlight them. That guy. So basically, what we did with the acetone, right, was we chose a wavelength where epsilon B was 0 and epsilon C was 0. Does that make sense?
Oh,
Miguel?
it's
Oh yeah, we did for that part where they were at 285. Only
Right.
acetone was present with
like the kinetics thing.
Oh
Yeah.
gosh.
Hey,
Is
you
that
saw?
from Pecan Lab?
Well, also just Gen Chem, but
Okay, got it. Yeah. Yeah. So basically, you know, we have these three components and we can get the concentration of acetone by using a wavelength where those oops, where these extinctions are 0. You know, and so we got 1%, and we got exactly 1%. We got exactly 1% for the concentration of acetone. Yeah. So now, if we want now to get the concentration of B, component B, which is toluene in this case, it used to be benzene, right? Acetone, benzene, and the third component was chloroform. Everything worked, but benzene and chloroform were too toxic, so I scrapped them.
thanks.
But benzene's really not toxic, but that's okay. Chloroform can get a little nasty after a while. You know, it used to be a major anesthetic. I mean, it was used, and you can give some people you can basically have them drink like 100 milliliters of chloroform, and they get a headache, but they're fine, you know. But anyways, so so now, what can we do to get to the concentration of, say, component B here, right? Now, spoiler alert, there is no wavelength where epsilon of A is 0 and epsilon of B is non-zero. Does that make sense?
Yeah.
What I'm saying is that the spectra of acetone and the spectra of benzene overlap. They overlap completely. Yeah?
Mm-hmm.
So but there certainly are wavelengths where the third component, epsilon C, is 0, right? So we can find a wavelength where epsilon sub C is 0 and only epsilon A and epsilon B contribute. Let me do this weird thing here. Video. Now, Gavin. No, Alexis. What wavelength, at what wavelength ranges are epsilon B and epsilon C 0?
It's like from 270, like 280 and up.
280 and above. Perfect. Okay, so now, and this is useless for determining the concentration of component B, right? Because 0 times 0 equals 0, right? There's no information. But if we want the concentration of component B, we can use 268 nanometers here because of what important fact, Leo?
Because acyl acetate is 0 here, and there's only acetone and toluene there, and you got the concentration of acetone from the first equation, like the graph after 285. So you can
Exactly.
figure out acetone. So for here, you just take out the concentration of acetone. All that left is toluene.
Oh my God, that's true. So probably that was way more coherent than I could ever have put it. Nicole, Alexis, did you get that? Did you understand that?
Yeah, that made sense.
You got?
Yeah, so he basically said take the difference at that exact wavelength to be left with 12.
Exactamundo. Okay. Abby?
Yep.
Excellent. Vincent?
Yes.
Gavin? Oh, Gavin says, yeah. Excellent. Cool. So I'm going to go back to the share. Bobbity, right here. And so what we're going to do is we're going to change the wavelength here to 268. Epsilon C at 268 is what value, Abby?
Epsilon C at 268 is what you said? And C is supposed to be
Ethyl acetate.
ethyl acetate, which is the blue one, right?
Get the color.
Okay, sorry, it's just because this is the only one we're looking at.
No, blue is acetone, I think.
Oh, you're
So
right.
ethyl
acetate was orange.
Yeah.
It was orange. So you're asking what the
Extinction coefficient is at 268 nanometers.
Isn't it going to be like, it's going to multiply to 0 at that point?
Yes.
Isn't it?
Yes, it's approximately 0, right?
Yeah.
So we can basically line it out here. Boom. Oops. Well, we can't let it out permanently, apparently. Whatever. Boink. So now we know, so now we have an equation with absorption of the mixture. Do we know that? Abby.
I'm sorry, what?
Absorption of the mixture at 268. Do we know that?
I mean, we should be able to look at the graph and see it.
Yes, we know that. Extinction coefficient for acetone at 268 nanometers. Do we know that?
Yeah, we know the absorption.
Yes, we do. So we calculate the extinction. Exactly. Concentration of acetone.
That's
we
the
know
1%.
that? That's 1%. Exactly. So we know this whole contribution here, right? Epsilon of second component, toluene at 268. Do we know that? Miguel.
Yes.
Excellent. We can calculate that. Concentration of toluene. Can we calculate it?
Didn't we calculate it at 0.025? Or is it-
Yeah, we did. But here we're doing it. What we're going to do here is we're going to say, let's see here. I'm going to drop the B's because they're all a bunch of ones. So it's going to be this guy minus this guy and this whole thing divided by and I'll be consistent dropping the B's here, even though it doesn't make any difference. Does that make sense?
Yeah.
And now when we've done this, we have two components, two of the three components. And now all we need to get the third is a wavelength where the absorbance of ethyl acetate is non-zero and non-ridiculous too. And the absorbance of the other extinctions are known, right? So the extinction of ethyl acetate, extinction of benzene, extinction of acetone or toluene and acetone. These three are known, and then we can calculate it for the mixture. Okay.
Makes sense.
Does that make sense? Okay, cool. All right. So now, would it surprise anybody here if there was a cool tool in the Excel toolkit that can do all this for you? Answer. Why, no, it would not, Dr. Taro. It would not surprise me at all. So there's a couple tools we can use, right? We can choose those. We can choose three wavelengths, right? And we can do what we just did, or we can solve it using matrix math.
Ah,
Yes, yes. We have a little matrix of absorbances, a little matrix of epsilons, and a matrix. And what we're trying to do is calculate a matrix of concentrations. And what that requires is inversion of this matrix, right? And if there's a lot of zeros in this matrix, right, then inverting it is easier. I mean, not a lot of zeros, but off diagonal zeros.
bold of you to assume I remember how to do matrices.
Well, I give you a good tutorial here, I think.
Okay.
So here's for example, you basically all you need is 3 wavelengths, and you get the 3 extinctions, right? And then you type M inverse. So it's you type M inverse and control shift enter, and then that will get you the answer. And then you multiply that by the absorbance. That gives you concentrations. And I know nobody got that. That's okay. You can read it here. But the last thing you can do is you can use linest, which essentially averages over all those possible matrices. And it doesn't actually average over them, but it actually uses the least squares approach that we talked about earlier. And and the only thing that I want you to take care of when you do this last approach is if you can remember to if you can remember to not include noise or distorted data. And I'm going to show you what I mean here. Okay. So why don't I go ahead and I'm going to do this right now. Are you guys ready? Okay. All right. Oh my God. Okay. So I'm sorry. I think I'm probably a little bit anxious because I've gone beyond all of our attention spans here. And I just want to watch me like I'm a stupid YouTube video and you don't have to learn anything. You can just sort of stand around and be critical. And then we can go over it again, right? So A equals epsilon C, right? That's the basic. That's the basic formula, right? So now we're going to use linest to get that data, right? And I'll do it. Actually, I'm not going to do it wrong. So now I'm going to format this axis here so we see everything. So minimum of 200, maximum of 400. Okay. So this is actually the data that we took. And there is a lot of problems with these data, right? The first problem is that at wavelengths that are shorter than 230 nanometers, these absorbances are off scale. So the standards are, and the mixture are messed up at wavelengths below 230. So we cannot use them when we apply linest. And then wavelengths above 325 are 0. So we can use them, but they don't help when we apply linest. Okay, so let's try to go from 230 to 340. 230 to 340. Now I'm going to make a, I'm going to highlight 5 rows, 1, 2, 3, 4, 5, by 3 columns. Yeah?
Sure.
Okay. Yeah. Now I'm going to come up into the formula bar. I'm going to equals linest. And the Y values are the mixture absorbances. Unknown absorbances between 230 and 340. So I'm going to come down here to 340. Where's the mixture absorbance? That's right. 340. And I'm going to go down, but not that far. I'm going to come back up to 230 here. There we go. Right? So there's the Y values. That's from 117, 63 to 117, right? Now I'm going to put in the X values. The X values are going to be these three epsilon values. So starting in row 63. And then we're going to say no constant and yes on stats. And then we say the only important thing here is that when I do shift control enter. Right? And that gives us the concentration, CA, CB, CC, right? And the uncertainties of these values, right? Okay. So CA came out to 0.12. That's pretty weird. Should have been
Wait,
exact.
how's it all three if you only compared two things?
Right. Because it's basically what it is, it's a whole bunch of iterations of this formula. Every wavelength is a repeat of that same formula.
Okay.
You got 285, 286, 287, right? And so every time for every row there's a new formula. And so you can get not only the concentrations, but you can get the uncertainty. Y, yeah. The Y is the absorbance. The X is the extinctions. And then the solution is the concentrations. Yeah. So I don't quite understand the answer I'm getting here, but that's okay. But so anyhow, there's the mechanics of how to get the answer. And I may have a correction to this video or to this coming out shortly. But I think that's probably enough for today. Try to get through the selective elimination part for say this week. Then we can go from there.
Okay.
Are our brains full?
Yes. Tired.
Okay.
And this is for the UV-VIS lab, correct?
Yes. Yeah. It's going to be, so just for y'all's information, I'll make an announcement. There's only going to be the one long lab for the whole semester. And we'll do probably 4 short labs, and then that'll be it.
Sounds good.
And you said you're going to give us the data for this
Yes.
later?
Yeah. I will give it to you probably right away. Oh, and yes, exactly. Yes, sir. All righty. Any
Sweet.
last questions? Yeah.
No.
Okay, folks. I will see you all tomorrow morning if you come to lecture, and I'm going to work on getting videos out there.
Okay.
Alrighty, guys. Thanks a lot.
Thank you, Dr. Turrell.
Bye.
Bye.